Hello, welcome to EEE 117. This is another part of chapter 10 where we're going to talk about mutual inductors and capacitors and their interactions together. All right. So the first thing we're going to do is kind of a little review of inductors and capacitors and their impedances. So remember, this is an inductor, Jx of L, and then impedance you could figure out is Jx of L is equal to J omega L, or omega is the frequency of the circuit. L is the value of the inductor in henries, right? The impedance of capacitor, on the other hand, or the capacitor itself here, is part of the circuit, and it's negative Jx of C, where impedance of this capacitor is negative J1 over omega C. Again, omega is frequency of circuit, C is the capacitance in farads, right? Now remember, an inductor is a magnetic field that you need to, with the AC source, you need to always build up and break down the magnetic field because it always opposes the change in current. That's how it built. That's why it's considered impedance, because it's always impeding the flow of the current. The capacitor, on the other hand, always resists the change in voltage with an electric field. So anytime you try and change the voltage, it's impeding your voltage change. So you still have to spend energy building and the collapse in the electric field in the capacitor. So there's some impedance, the equivalent impedance involved, the amount of energy and work it will take to build and break down both the magnetic field and the electric field. Okay. Now, what would happen if we add both of these together in series? So we have a capacitor and inductor in series. And what is the net impedance? Well, remember, because they're impedances now, we could treat them like resistors. So in series, we could just literally add them together. So you can have a negative Jx of L plus a negative Jx of C. And when you when you break it down a little bit, you could say that, well, your inductor impedance is J omega L and your capacitor impedance is negative J1 over omega C. So you can see that the inductor is a positive and a capacitor is negative. So there could be a point where you could control the total net impedance of the circuit. If you could choose L and C wisely, you could actually zero out this impedance. Or you could change impedance by changing frequency of the circuit from the source. So capacitors and inductors have a very unique interaction between them, right? That we're going to explore today. So again, let's put them in series. What ends up happening impedance-wise? Well, one's positive, one negative, they actually cancel each other out, right? So from a circuit standpoint, if I have my Jx of L, my impedance of my inductor is J10 ohms, what impedance will make the capacitor, what impedance can we have of the capacitor to make the total impedance zero of the circuit? Well, I could easily make a capacitor with an impedance of negative J10 ohms, right? Because all capacitors have negative impedance. So my total impedance, adding them together because they're in series, is a positive 10J and a negative 10J, which is a net zero. So by carefully selecting the L and C together, we could have a phenomenon called a zero impedance circuit or a series LC resonance. L for the inductor, C for capacitor there. Resonance is another way to say cancellation, right? Or they're in tune with each other. So the inductor and capacitor are perfectly tuned that they're canceling each other out because the energy is oscillating between the two. It's just a very unique, strange phenomenon. People figured out that individually, inductors and capacitors have an impedance, but when they're together, they end up not having any impedance, right? So this drastically changes the circuit. So of course, the big question is how do you cancel impedance? That doesn't make sense right now physically. So something must be going on from a physical standpoint for these things to cancel out. So we got to put our physics caps on and ask ourselves, well, what's actually going on? So number one, if we want to change inductor current, what do we need to do? Anytime this inductor, if this magnetic field needs to change, we need to either add or take out if the current through the inductor changes, we need to change the magnetic field around the inductor. So remember, an inductor has a magnetic field flowing through it. And anytime we want to change a current, we need to pay a tax and put energy or absorb energy out from the magnetic field. It's always there to stuff us. Okay. The source always does that at a cost, but we can do that. All right. So the AC source wants to change a current, and the inductor will oppose this change. Act like an impedance. That's why we have impedances with an inductor. Now, if you have a capacitor nearby, conveniently, a capacitor can fulfill the role of breaking down and building up the magnetic field of the inductor. Because remember, capacitor is just a bucket of energy ready to go in a moment's notice. So we can finely tune the circuit where the capacitor can dump its stored energy to instantly change a magnetic field. So think about any time a magnetic field needs to change, the capacitor is right there and say, I got you, bro. And then we'll dump the energy out to change a magnetic field, right? And it's tuned perfectly. So a series RL resonance is when the capacitor has exactly enough energy to instantly change an inductor's magnetic field. It's not too much and it's not too little, because if we had too much energy, then the capacitor will act like an impedance because it has leftover energy. If it doesn't have enough energy, you didn't fully change the magnetic field, so the inductor will still have a little bit of impedance left. So it's perfectly tuned where if I need 500 units of energy for the magnetic field, the capacitor immediately has exactly 500 units of energy, and they're swapping energy back and forth between the inductor and capacitor. And they just do it back and forth forever. That's how I like to imagine it. It's like playing ping pong ball with energy. For one split second, the capacitor has the energy, and then it bleeds it all into the inductor to change the magnetic field. And then half a cycle later, the inductor has that energy and it needs to let go, so it puts it right back into the capacitor. So it's kind of a placeholder where energy is swapping back and forth between the electric field of the capacitor and the magnetic field of the inductor. And it's doing it so perfectly that the source doesn't need to do anything. It's kind of almost a perpetual, can't say it's a perpetual motion machine, but it's so close where these are very efficient devices, this could go back and forth for a very, very long time, right? This energy swapping. Very strange phenomenon, but we use it to our advantage every so often in circuit design. Okay, so this is a series resonance. Okay, now what happens if we have a resistor nearby? Because more realistically, we're not just having an inductor and capacitor, we're going to have a load attached to it also, a resistor. So traditionally, a load you see in a power system is a RL load. So there's typically a resistive and an inductive component for most loads in the system. What's impedance of these together? It's a R plus JXL load. Okay. Now, one way we could fix this is if we put a capacitor in series with this load, we could kind of cancel out that inductor a little bit and make the system a little more efficient. Because remember, we keep talking about this inductor. It's not doing any real work. It's kind of like a tax we have to pay to keep the load running. And I don't like taxes. I don't like wasting energy on a magnetic field if I don't have to, especially if I'm not getting work done with it. So we could install a capacitor in series where the inductor and the capacitor impedance might cancel out a little bit. So all we're left with is the resistor, which increases our efficiency. It gets rid of reactive power Q and raises our power factor, right? And that's kind of an advantage of a series resonance. It helps us cancel out inductors and be a little more efficient. So typically, you'll see all three put together, a R, a C, and an L. So it's called an RLC circuit and it's RLC series resonance. So here we're going to do a little example problem where we have a voltage source, 120 volts, angle 0 degrees RMS. Capacitance is C equals 0.2 millifarads. The inductor L is 5 milliohms, and the resistor is 5 ohms. The inductor is 5 millihenries, and the resistor is 5 ohms. If our system is running at 1,000 radians per second, calculate the total impedance of the circuit. See if these two cancel out. Well, you can just do them one by one. Jx of L is JWL. W is 1,000. L is 5 milli. So it's just J 5 ohms. The milli and 1,000 cancel out. That way the numbers are easy to work with. What about the capacitor? Negative Jx of C. So it's negative J 1 over the omega C or WC. Negative J is 1 over 1,000 times 0.2 milli. So negative J is 1 over 0.2, which is negative J 5 ohms. So you can already tell they're going to cancel out because remember, we add them all together. So add them all together. They're in series. So it's R plus Jx of L minus Jx of C. So you have 5 for the resistor, positive J5 for the inductor, negative J5 for the capacitor. And these two J components cancel out when we add them together. So we're just left with 5 ohms only. So this circuit, exactly at 1,000 radians per second, is where both inductors and capacitors cancel each other out. They're in that perfect series resonance where they're just swapping energy back and forth between each other, and nothing else in the circuit matters except for the resistor. Okay? So just wanted to show you kind of the math behind it, just paying attention to impedances. Again, you always have to pay attention to the J component, and everything else should be pretty straightforward, right? Now, we notice that there's a very specific frequency where these two capacitors and inductors cancel each other out. Can we find the exact frequency if we don't know it, right? Well, let's say we have V equals 120, angle 0 degrees, F equals 60 hertz, right? Now we need to find C. Let's say I want to have a series resonance as F equals 60 hertz. I want you to tell me the capacitance that's needed to do that. Well, we could figure it out. Doing some little math tricks I don't want to waste time on is we could find a specific resonant frequency which is equal to 1 over the square root of LC. So as long as you know 2 out of 3 of these numbers, you can immediately figure out the third one, right? And this 1 over square root of LC is very, very common as a resonant frequency calculation. I've seen this many, many times in circuit books. Don't forget this is radians per second. So if I gave you frequency, right, WR has to equal to 2 pi F. Now, for this particular problem, if I need C, I could just swap things around. I could square both sides to get rid of the square root. So we have WR squared and swap WR with C. And then we have over here, capacitance equals 1 over omega WR squared times L. And at this point, it's just plug and chug, right? But as long as you understand the cancellation effect of a series resonance, honestly, the math isn't too hard. Some square roots and squares here and there, but it's nothing too crazy like triple integrals and blah 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 blah, right? So just wanted to try to show you very simplistically what's going on in RLC circuit. It's literally just capacitors and inductors canceling each other at a very specific frequency. Now, if our frequency is not, if we design our system and then the frequency changes to 120 hertz or 500 hertz, then they're not going to cancel each other out. Remember, the RLC circuit only cancels at the frequency you choose. Any other frequency is going to do other things. Okay. Now, if the frequency is 60 hertz and we move to 61 or 62 hertz, we're just a few degrees off. There technically will be a capacitive or inductive impedance, but it's going to be pretty small. But the further away we get from this resonant frequency, the inductor and the or capacitor gets bigger and bigger and bigger, right? So think about the resonant frequency is a perfect point where you have the lowest impedance, and anywhere past that going to the greater or less the frequency, the impedances rise up. It's kind of like a V shape where the bottom of the V is a perfect resonant point, and the impedance kind of grows higher and higher in both directions, going higher and lower frequency. Okay. So let's go ahead and do a little calculation for RLC circuit here. I'm giving you V1 is 227 angle 0 degrees VRMS. F equals 20 hertz, L equals 10 millihenries, R equals 5 ohms. Go ahead and calculate I1, apparent power S. So if we've done this about 5 times, now it shouldn't be too hard for you. And then coming down here, adding in a capacitor, calculate the capacitance C. for a RLC resonance. So I want you to tell me what capacitance in farads is needed to have this resonance at 60 hertz. Okay. And then I want you to calculate the new apparent power S of the circuit as these two impedances cancel out to see how much more power we can get out of it. Okay. So let's take our 15-20 minutes break, and we're going to come back and see what you can do or what you did and check answers. So pause this video and we'll catch you in a second. Hello, welcome back to EEE 117, Chapter 10, where we're going to continue talking about series RLC circuit. So you just did an exercise on it, and we'll go ahead and check out the answers and see how you did. So let's go ahead and scroll down. So first thing we can do is to calculate the total impedance of the circuit. You have Jx of L, so it's an inductor and a resistor together. So calculate Jx of L is J omega L, where omega is 377 radians per second. How do I get 377? It's always 60 hertz. 60 hertz times 2 pi is equal to 377 radians a second. So J377 times 10 milli is J3.77, right? Now the current flowing through the circuit is going to be your voltage divided by your net impedance, which is R plus JX because they're in series. So V1 divided by R plus JX, where it's a phasor. So V1 is the 277 angle 0 degrees, volts RMS value, divided by 5 plus J377, where 5 is the impedance of the resistor. Number crunch out real quick, and you're going to get 44.2 angle negative 37 degrees in amps RMS. Now, let's calculate the apparent power S. So just the magnitude, that's just VRMS times IRMS, which is 277 times 44.2, and that's 12.24 kVA. So this whole circuit is delivering 12.24 kVA. So I'm just going to the inductor, so I'm just going to the resistor, right? Now, we could use the RLC, the benefit for our RLC circuit by adding in a capacitor to cancel out the inductor. Remember, RL circuit, that inductor most likely is just there because we can't help it. Think of it like a motor with a magnetic field that we kind of have to use a magnetic field to make a motor operate, and we can't get away from it. But we could put a capacitor nearby in series with it, and that will help alleviate the energy draw of the magnetic field, because the capacitor will have the extra energy in its electric field to dump into the magnetic field of the motor, so they kind of help each other out and lighten the burden on the source itself. So calculate the capacitance for a series RLC resonance. So remember, omega R, which is a resonant frequency, is equal to 1 divided by square root LC. We know L, we know omega R, that's 60 hertz, or 377 radians per second, right? Because the circuit is running at 60 hertz. So we want to make sure these two L and C components resonate at 60 hertz. Otherwise, it won't work. It won't get the full benefit of cancellation. So just swapping and doing some arithmetic, squaring both sides, swapping the WR squared and C, you get C equals 1 over omega R squared times L, right? So C is now equal to 1 divided by 377 squared times 10 milli, where we have 0.7 millifarads, right? So that is your net capacitance needed to have that exact RLC resonance at 60 hertz. Calculate the new impedance, or the current. Current is just I equals V1 over Z, where Z is now 5 ohms because we canceled out the impedances of the inductor and capacitor. That's the whole point of series RLC resonance. So it's plus J0. Naturally, we're going to have more current, 55.4 angle 0 degrees. So we get more current flowing through the circuit because the impedances of both the capacitor and inductor are gone. And so naturally, we're going to get more power to the resistor. So S equals V squared times I squared, where V is still 277, but now the current is 55.4. So by lowering impedance, we let more current through, so we're getting more net power to the resistor by using this series RLC resonance. And that's a big advantage, because now I could get more. Number one, you get more power to the load. Number two, None of this is reactive power because there is no the J is zero, so no reactive powers in the circuit. Additionally, there's 0 degree phase shift between the voltage and the current. So this is a perfect ideal 1.0 power factor unity load, which is kind of exactly what I want. Okay. So that's the series one. Let's talk about a parallel RLC circuit. So very similar idea, except what happens when you put the capacitor and inductor in parallel? Do we still get the same properties and the same physical phenomenon as a series LC circuit? So different types of resonance can occur when you put a capacitor and inductor in parallel. So what's happening here? Well, first off, what is the total impedance of two devices in parallel? So our Z total is going to be 1 divided by the impedance of the capacitor. So it's 1 divided by negative Jx of C plus 1 divided by Jx of L. And then you take the inverse of all this put together, right? This is your generic parallel impedance adding two impedances in parallel formula. Now, there's a shorthand trick that instead of doing this inverse of inverse, blah, 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 it's just one element times another element divided by one element plus another element. So you've probably seen this where it's R1 times R2 divided by R1 plus R2. You can use the same thing for the L and the C because they're both in impedances. So the top part, you multiply them together, you got 1 divided by negative Jx of C, multiply them together times Jx of L, right? I'm sorry, quick mistake. Technically, this should be negative J. No. Yeah, it's fine. We could just keep going. If it's a small mistake, who cares, right? So we'll take this. It's bothering me. So it should be negative Jx of C times Jx of L, right? I just put in 1 over divided by accident. My apologies. Okay, so now this is correct. So it's negative Jx of C times Jx of L divided by negative Jx of C plus Jx of L. So the top is multiplied together, the bottom is add them. Okay. Now, remember the whole point of a resonant is canceling impedances out. So what happens if I have XC equal to XL? What if I say, well, if I take negative Jx of C plus Jx of L, and I put both X of C and XL to 10 each, 10 ohms for both, they're going to cancel to 0 ohms. That's what a series resonance did. We could use the same phenomenon where this cancels to 0, but the big difference is, look, this is in the denominator. So what ends up happening is you got something divided by 0, which we know is infinite impedance. So very big difference in this particular case. This now turns into an open circuit rather than a short circuit. See, a series LC circuit, they cancel each other out to be a short circuit. Here, they're kind of canceling each other out, but what they're really doing is the capacitor and inductor are tuned perfectly together that they don't need any energy from the source. So from a source's standpoint, it looks like it's an open circuit because there's no current flowing to the capacitor or inductor. So circuit-wise, it's an infinite impedance or an open circuit, right? So let's kind of ask ourselves, well, I guess I answered a question here, but we'll go over it again. When capacitor and inductor impedance will cancel out, what is the result of the circuit? The impedance is infinity or an open circuit. So from the source's standpoint, it acts like these two devices don't even exist anymore. And it's just open lines. Okay. What's this phenomenon called? It's called a parallel LC resonance. So it's kind of opposite of series one where this is now open circuit instead. Okay. Now, of course, the big question is, how does this even work? How do you make something infinite impedance and then turn it off from the circuit? Well, let's go and do our same analysis again. So because we're talking things because now we have things in parallel, let's think of the capacitor. The capacitor now is trying to fight the change of the voltage. So if the source wants to change the voltage because it's an AC source, right? So it's moving up and down. Give me a second. Okay, so the AC source has a positive cycle, negative cycle. So both the capacitor and inductor will both have the same voltage. So if we ever try to change the voltage, the capacitor is going to be the one fighting it this time. So if ever want to change the voltage in the capacitor, you got the change amount, you must change the amount of energy stored in the capacitor. So every time I change a voltage, I either need to take energy out of the electric field or add more energy into electric field. So it takes a little bit of effort to change a voltage across the capacitor and the inductor because they're both in parallel. Okay. When an AC source wants to change the voltage in the capacitor, we must absorb or supply a lot of energy from the circuit. So that's the capacitor saying, feed me or take the energy out. That's what you need. That's a tax you have to pay to change the voltage across the capacitor. Conveniently, if we need the energy, there's an inductor nearby with a magnetic field to either feed or absorb the energy that the capacitor wants. So as we try to change the voltage, instead of dumping energy into the capacitor from the source, the inductor is nearby and an inductor will dump energy into the capacitor, right? So conveniently, an inductor can fulfill the role to help the capacitor, and the inductor can act like a sponge to instantly absorb or supply energy to the capacitor. So the capacitor has a bunch of energy to spit out and pull back in, really back and forth a lot. And the source is trying to, it takes me some effort to give you energy and dump it in and out instantaneously. But then the inductor is nearby saying, hey, bro, I got you. I got this energy in my magnetic field that I could help absorb or take in energy from you. Right. So just like the other series RC circuit is the same philosophy is the energy is going to just go jump back and forth between inductor and capacitor and ping pong forever. Right. So in a parallel RC resonance, the inductor has just enough energy to instantly charge and discharge a capacitor. So they're both self-sufficient. So in a perfect world, if this is a very efficient system, the energy is going to ping pong between inductor and capacitor forever, and we're not going to get anything from the source. So the current I1 will be equal to 0. And that's why we have is considered infinite impedance, is when you have a voltage, you have 0 current. That must mean you have infinite impedance to make that happen, right? Okay. So now we kind of have an idea of physically what's happening. Let's dive into a little more of the circuit to see how can we use this to our benefit. Well, again, normally we have a load on the circuit. It could be a RO load, for example. So you have a resistive load and inductive load side by side. Again, this could be a motor or another piece of equipment in an industrial plant. So it's very common to have an inductance near a resistor. If we want to lower impedance of the circuit, we can add a capacitor, if we want to change impedance of the circuit and make it more efficient, we could add a capacitor next to an inductor side by side in parallel. And what happens is both of these feed off each other, and now you have infinite impedance right here, right? So in essence, all the current is now just going to flow through the resistor, not waste its time going to an inductor or the capacitor, right? Which is good because the less current flowing through the capacitor and inductor from the source, the more energy I can save, right? So again, this is an energy saving technique, right? So creating parallel resonance was a resulting impedance. Well, since the capacitor and inductors are both infinite, the current will never take its path. So you can even cross these two branches out. So only the current is going to flow through a resistor, and so Z of the circuit now is just R resistor. So we went from a JXL plus R to just a R, which we made the circuit more efficient by eliminating the inductor with the nearby capacitor. Okay, that's the power of an LC parallel resonance. Now, of course, the big question is, well, what's happening between these two? Are they just like off of their own world? Yeah, kind of. These two devices are kind of ignoring the rest of the circuit, and there's a little bit of reactive power oscillating back and forth between inductor and capacitor. And it's going to forever do this, right? So they're perfectly in tune in that resonant frequency, and just energy is ping-ponging back and forth over and over and over again. And then the source and the resistor is just getting ignored, right? Now, did we cover this before? Right? So the Q source is 0, which is better than previously where the source, if we didn't have the capacitor, the source would have to send reactive power to the inductor. Did we ever cover this before in the last chapter? And it's called, yes, we have. This is the physical phenomenon we call power factor correction. We talked about having a capacitor nearby to make reactive power go to zero for the source. Now, the physics, what's happening, you see here, is an inductor is there supplying the reactive power, sorry, the capacitor is locally supplying power, reactive power to the inductor. So they're like this, their own self-absorbed efficient, absorbed system in the corner, where now we just have the resistor with real power, a real power P. And that's exactly what power factor correction is. It's a fancy, easier way to say RLC resonance. Technically it's a parallel RLC resonance. That's exactly what we were doing before. Okay. So what about in terms of the actual resonant frequency? So now we see a benefit of using this. What if we need to design a circuit for a certain omega C or omega resonant, or we need to figure out a specific capacitance to force this circuit to resonate at 60 hertz for power factor correction? Well, remember, one of the key components of RLC circuits is a resonant frequency where both the capacitor and inductors cancel out. And parallel-wise, they cancel out by having infinite impedance. What is the actual, how can we relate resonant frequency to L and C, which is omega equals 1 over LC. Very simple. It's the exact same as the series one, except it's parallel now. Okay. So compared to series resonant RLC circuit, is there any difference? The only difference is you put the L and C in parallel for parallel RLC resonance. And then for series RLC resonance, you put the inductor and capacitor in series. But circuit-wise, the math, they're all exactly the same, because technically it doesn't matter where the capacitor and inductors are. As long as they're nearby, they're going to cancel each other out every time. Okay. And so that's pretty much RLC's resonant circuits. It's again, I always want to take this really complicated topic, kind of break it down to more simplistic physics terms so we all understand, and then the math kind of crunches in nice and neat. Right, so just a summary is you have a parallel RLC resonance where both the resistor, inductor, capacitor, they're all in parallel, right? A series RLC resonance is where the inductor, resistor, and capacitor are in series. For both of these circuits, the inductors and capacitors, their impedances always cancel out. In series, they equal to 0, so they're out of the circuit. In parallel, they're both infinity, so the current ignores them and goes straight to the resistor. Either way, at the end, the source does not see inductors or capacitor anymore. It's invisible to the circuit overall. Okay, the resulting impedance of the parallel RLC resonance is the whole circuit is just Z equals R, just a resistor. For a series RLC resonance, the impedance of the total circuit is just R, the resistor, because the L and C canceled out. Now, remember, this only is applicable to the exact resonant frequency we design. Anytime we go away from the resonant frequency, this Z is going to have an inductor or capacitor value added onto it. And the further away we go from resonant frequency, the bigger that J component is going to get. Okay. So we want to make sure our circuit is acting exactly at the resonant frequency, which is what we designed for. So we can calculate this as a resonant frequency equals to 1 over square root of LC for both circuits. Okay. So that's pretty much all I have for these RLC circuits. I hope I did my job a little bit good enough so that you understand it a little bit more than before. And go ahead and review the problems here. If you could do the exercise again, there's going to be the homework quiz and the quizzes for you to practice on. This is one of the hardest concepts, and a lot of young electrical engineers, it's hard for them to understand. But if you break it down into simpler concepts, kind of like save the summary sheet, save these notes, when you see it again in electronics and other courses, hopefully it'll be a little bit easier to understand then. And then over the course of years, it'll make more sense as you keep using everything. Okay. So thanks for showing up. Hope you guys have a good rest of the week. We'll always be here next week to cover the next topic of circuits for you. So thanks for showing up. You guys have a good afternoon or night.